Okay, so we are almost done with course material. We have 10-2 today, so we're hypothesis testing some more. So last time we talked about the null hypothesis and alternative hypothesis. We're going to be using those again today and building on it a little bit. So now we're going to finally see why we do what we do. Couple equations that we're going to need. These are all things we've done before. So our z-score, our standard deviation. So we're doing proportions. So that's our standard deviation for proportions. No, it's been a minute. Yeah. All right, so 10-2. All right, so hypothesis testing for proportions. I have a not super long definition, but long enough. So it is something called statistically significant, and that is really hard to say fast. Whoops, that's not how I spell that. So let me give you the definition, and then I'll kind of break it down a little more. So this happens when observed results are unlikely under the assumption no hypothesis is true. So then when that happens, we reject the null. That's our H0. So last time we spent a lot of time talking about the null hypothesis. If you recall, the null is we assume there's no difference in our population. So now we're comparing statistics. So we say there's no difference. The population parameter is what we said it was, nothing exciting happening. So if it's statistically significant, this is anytime you run a statistic, you're probably going to get something that's different than a previous person who ran a statistic because numbers just don't pop up the same all the time. But this says, okay, we have a difference. Is our difference big enough to not be chance, to not just be the luck of the draw? So that's what we're looking for. And this, what we're going to do with this in the next couple sections is how do we know that? So is let's So if you remember our z-score, our normal distribution, we had, let's look within 2 standard deviations. It's the 68, 95, oops, 59.7 rule. That was early days, first, second week of class, we talked about this. Basically, what this rule said was if our numbers are normally distributed, we expect that 95% of the population will be within 1 standard deviation of the mean. So we want to two standard deviations of the mean. We want to make sure our numbers are even more different. So we want to be more than 2 standard deviations away. If not, it's due to chance, most likely. So I said, let's look at slide. There we go. So we have a politician who hires a polling firm to obtain a random sample of 1,000 registered voters in her district. She finds that 534 are in favor of the policy. We get our population proportion, 534 divided by 1,000, 0.534. So we assume our population is 50. Or if our mean was 50 and our, hello brain, our p hat was 0.534. We can use our standard deviation equation, which I gave you at the start. And that is going to give me, I cheated a little bit, 0.016. So if we take our mean and add a standard deviation twice, what do we get? Well, right here, 0.516. We add it again, 0.532. We also want to subtract the standard deviation. So we subtract it twice. And I said 0.484, 0.468. So that's within 2 standard deviations. I made a really bad drawing. I'm so sorry. Our data value we found was 0.534. So if we look at our standard deviation, the highest one we have listed there was 0.532. So our data value is over here. Our data value is more than 2 standard deviations from the mean. So at the moment, we're going to say that's unlikely due to chance. We're going to have a better way of analyzing this, but for now, it's kind of what we're looking at. How far away are we from the mean? Is this what we think it should be? Okay. If we want to be slightly more formal, we find the z-score. So that is going to be our calculated number minus our mean divided by our standard deviation, and 0.534 minus 0.5. That's 2.13. So we can find our z-value, which again measures how many standard deviations we are from the mean, is bigger than 2. So we're farther than 2 standard deviations away. So we are going to reject the null. And the null would have said there's no difference in our population is exactly what the 50%. So we reject the null, we have evidence towards our alternative hypothesis. Okay. Let's be a little more formulaic about this and have a better plan. So we have 2 approaches we use. The first one is the classical approach. This is what I learned when I learned statistics way back when. For our classical approaches, we take our data values, we find our z-score. And then we're going to compare it to a z-crit. And this is based on our alpha level. So if we want to be an alpha 0.05, we want to be 95% unlikely due to chance. So we would look up that value, and I have a list of those I'll give in a bit. So we want our Z value to be bigger or smaller, depending on if it's positive or negative. So if our Z is positive, it's significant. If Z is greater than our Z crit. So we have to be bigger than our Z crit. If you remember our little picture, our Z crit's going to be here-ish, and we want ours to be farther away from the mean than our critical value. If it's negative, we go the other way. In this case, we would make our Z crit negative. So it's a plus or minus sort of thing. So we want to be farther away. So again, farther from the mean is what we want to be significant. I feel like we've done some of these before a little bit. We haven't hit them hard, but I feel like we hit these before. The other approach, which is similar, is called the p-value approach. And I have some examples after this. Unfortunately, we have p-value and we're looking at a p-hat statistic. Our p means probability. It's not the same as the p-hat. So for the other things where we look at different, like we'll look at means, we'll look at other things, we'll still have a p-value approach. Sometimes things get named the same. So here, we're going to use our statistic. Likelihood. Our data. Hang on, I left out a word in my notes. So we're looking at the likelihood that our data is just due to chance. So if we were to run another sample with the same group, we would find something closer to our mean. So we want a small z, or p-value. Okay, so building on the previous example, we found our p-hat was 0.534. Fancy P just means probability, so it's a bolded P. So we want the probability that this is due to chance. Really tired of drawing these today. So our number was higher than our mean was 50. We want the probability that something due to chance is in this tail. That's our goal. How do we do that? We've actually done this before. We're just going to put it all together. So step one, we're going to find the z-score. So we have our formula for that. I gave it earlier. Step two, probability our z is greater than whatever value that was. So we look up the z we found in step one. Then we're going to report the p-value from our table, but we may have to manipulate it a little bit depending on which direction we're going. And finally, we're going to translate this into regular people words. Okay. So we said p hat was a value. Now we're going to look at our z-score because we have a table for that. So what is the probability our z-score is 2.15 or higher? Well, remember our good old z-score chart? Nope. Sorry, too many tabs open. All right, so we remember this guy. We love it. We hate it. We're going to look up our 215. So 2.1. There's 0, 1, 2, 3, 4, 5. The number there was 0.9842. We all see that? Okay, so the value from our chart was 0.9842. Oh yeah, I get to draw this again. So we know this is our z value here, so this is a z value of 0. Do you remember what portion of this graph the chart gives us? Does it give us the left side or the right side? Our z-score chart. In a minute. Left side, yeah, thank you. Yeah, so our chart is always going to give us the left side of our value here. So that says the area to the left of our z-score was 0.9842. So what's the probability we get our score, a z-score of 215 or higher? Well, the total area under the curve is 1, so we take 1 minus this. Getting the z-score of 215 or more is that the same? 0.0158. So the probability by chance of getting a z-score of 215 or higher is 0.0158. I always like to put it in percent terms because my brain likes percents. So it's a 1.58% chance we get this or higher. So do you think, is that a good probability? Is our data likely due to chance, or is it likely due to something else? Well, our probability due to chance is really small, so this is not likely to be due to chance. Okay, some of these. Yeah. -1 in these kind of cases, or? No, it depends on what direction. If you have a negative z-score, it's going to be whatever you look up. Okay. So it really depends on the problem, like what portion are we looking for? Do we want this or more? Then we're going to subtract. If we want this or less, the table gives us that value. Okay. That is a great. Positive, it's more likely to be a different number, or when it's negative, it's more likely to be a different number? When it's positive. When it's positive. Yep. So that is a great question though, because these are really funky. We always want the okay. So the question we had was, when do we subtract, when do we not subtract? Depends on our z-score. If we have a positive z-score, we're probably going to subtract. If it's negative, we're not. But let's kind of talk about why that is. I'm sorry, my picture is really lousy. I tried. So if we're in the blue zone, our theory is that our data could be likely due to chance. It's possibly not, but the likelihood isn't high enough. If we're in the little white zones to the side, the uncolored parts, those are less likely due to chance because the likelihood of being in the tail is low. So our table always gives us the area from the z-score we looked up to the left. So if I have a negative z-score, oh, that is really bad, sorry. It's just going to give us the little bit in the tail most likely. So in that case, we already have the picture of the tail where we want it. We would just take this as is. If we have the high zone, which is what I tried to draw over here, let me draw it again. Oh, yeah, they're getting worse. If we want to figure out that area, we take the left side minus. So that's the case where we subtract because it's in the high tails, high tail, low tail. Does that make sense? Did I answer your question? Okay. And once we get into the examples with these, it'll help cement it down too. We just kind of got to get through the vocab and the theory of it first before we can really. There's a lot of vocab in this section. And then it's a lot of, we're using P for two different things because. Proportions. Yes, yep. So usually for probability, we use big P, and then other things is little, but it's not always like exactly. Okay. So, oh, I didn't give this definition, sorry. The whole tornado threw me off. Okay, so this is big P, so value for probability. And this is the probability. I'm just gonna say prob of observing a sample stat as extreme or more extreme than the one observed. The probability that we get this one, or I don't want to say higher because we could do lower too, but farther in the tails than ours. And we want the lowest P possible. If we want the probability we get an odd sample to be low, because then that means our sample is significant. It matters. It's not just chance. Okay. So let's put this all together and do hypothesis testing regarding a proportion, so p hat. There's two different versions of this. There's the classical and the p-value. So steps 1 and 2 are the same for both. 3, 4, and 5 are different. So I'm not going to write steps 1 and 2 down twice because it's the exact same. Population portion. This is p hat. Sorry, I struggle with proportion. There's too many PROs in there. Okay, the first thing we want to do after we read through our thing and make sure this is the right test for us is determine our hypotheses. We haven't really done that yet, but that's okay. We will going forward. Okay. So determine our null and alternative hypothesis. So remember, your null hypothesis is there's no difference. It's what we said it was before. Alternative is there is a difference. When we write our alternative, this tells us how many tails we have. If our alternative hypothesis says that our proportion does not equal whatever, I shouldn't use alpha because we use alpha again, does not equal whatever, that is a two-tailed test. So we want to see that it's in either tail. If we have either proportion is greater than or proportion is less than, this is a one-tailed test. And in practice, sometimes it's tricky to tell which one is which. Worst comes default to the two-tailed, but most of the time they're going to say either greater than or less than. They'll tell you they think this thing is bigger or this thing is bigger. It should be pretty clear with homework and such. Okay. We determined that. It's our time coming off a little bit. Next thing is we select level of significance. And this is our alpha level, which is why I didn't want to use alpha before. Most of the time in our class, we're going to choose an alpha of 0.05. I honestly can't think of a case where I would use an alpha bigger than that. So like a 0.1, which would be the 90%. If anything, your alpha will get smaller. So 0.01 is common. I have seen 0.001. But most of the time for us, 0.05 is great. That's significant enough. Okay, here's where our steps are going to be different depending on approach. So this is the classical approach. Actually, no, step 3 is the same for both. Depending on how we want to think about this, our Z formula, which we've been using, is our P hat minus our P naught over our standard deviation. A lot of times they're going to give us all of these, like the P hat and the standard deviation, but sometimes we have to calculate it. So our Z score is going to be the same in either method. Steps 4 and 5 are what's different. Can I scroll past? Are we good? Okay, slow me down if you need to. At this point, we've looked up our Z-crit, so use table. This is where we'd read our Z-chart backwards. I'm going to give you the most common ones so you don't have to look them up every time. You'll get to know them very well. Then compare our Z with Z-crit. Your Z-crit can be positive or negative. It's going to depend on what our Z value is. If our Z value is positive, we'll use the positive Z-crit. If it's negative, we flip it around and use it negative because we just need to be farther away from the mean. And finally, state conclusion. And our conclusion should be, did we fail to reject the null or did we reject the null? You all familiar with absolute value signs? Distance from 0. So if our Z value, the absolute value of our Z is smaller than the absolute value of Z crit, we failed to reject the null hypothesis. Our different isn't enough to say it's not due to chance. When we reject, is when the absolute value is greater than. I have never had a case where it's equal, but I suppose if it's equal, we would throw it into the reject null hypothesis, just because it's unlikely. I said I would give you your common crit values, and I am. If we have a one-tailed test where we say ours is bigger or smaller, at our 0.05 level, our Z-crit is either going to be positive or negative 1.645. So that's, for a one-tailed test, what we're probably going to use. For a two-tailed test, and again, we're still at the alpha 0.05 level. Our Z crit is plus or minus 1.96. So that should save us some hassle of looking that up. And the classical approach, we don't actually have to look up our values in our Z chart. If we have our criticals, we just compare it and call it a day. Our p-value approach, we do have to look them up. It's a little for our p-value. Our step 4, we still find our Z. Now we're going to look up Z. And step 5 is still conclusions. This time we're comparing to our alpha values, really. Are we far enough away from the mean? Okay. Let's do an example. And we can use either approach with this one. So I threw my example, where was it? All right. Oh, they gave the game away, told us it's a two-tailed test. Okay, so this is a two-tailed test. I didn't realize they gave it away in the title. So we were asked, or our group was asked, which do you think is easier to raise, a boy or a girl? When asked the question in 1947, 24% said a girl was easier. In 2018, we have a survey, and 408 of our 1,500 adults said a girl was easier. Okay. So does it suggest that more Americans believe a girl is easier now or not? Let's analyze what we got. So our old data value, our P naught, 0.24. So that's from our 1947 data. Our P hat, I did not write that number down, did I? We have 408 out of our 1,500. So our new data, we get a proportion or percent of 0.272. They already told us this was a two-tailed. We also know it's a two-tailed because they said, is there a difference? They didn't say, is it higher, is it lower? They just asked for a difference. Okay, probably the hardest part of the section is stating our null and our alternative hypothesis. So I'm gonna let you attempt that. Do you want me to flip back to the example or leave it here? Example, okay. So here's our example again. What's our null hypothesis? Any takers, anyone brave? There's more than one way to say this. This is how I'm going to choose to say it. If you said it a different way, that's fine. It's the sentiment should be the same. So our null hypothesis is there's no difference in opinions between 1947 and 2018. So no difference. We're gonna say P equals our original data. So our alternative hypothesis says there is a difference. So we just say P does not equal 0.24 because the example didn't specify higher or lower, so we just say not equal. Those are the easiest ones. Okay. I'm not going to make you answer this yet, but think about why do we want to determine our alpha level so early before we have data? There's a really good reason, but I'll let you think on that and we'll come back to it. So we do need to determine our alpha before we do any sort of calculation beyond what we have. All right, so the Z value we have, I'm going to calculate it all out, 0.272 minus 0.24. For our standard deviation, we use the original data. All over 1,500. That's our current sample. All right, I'm going to skip some steps and just go straight to, so I know we can plug that in and do our thing. So we get our Z value 2.9. We should have looked at our Z crit before now, but once we've decided our alpha level, we can hold off. I gave you what the Z crit should be for this. What was that? Well, we have a two-tailed test, so I'm gonna, and our alpha is 0.05. What I gave us before, plus or minus 1.96. So let's translate this. When I drew these, oh, that's really bad, not symmetric, that's okay. I would always do, here's my Z equals 0. Here's my high Z, Z equals 1.96. Z equals negative 1.96. So since it's two-tailed, I have to draw both. So if we're in the tails, we're happy. We want to be in the tails because that means we have a difference. Our Z value was 2.9. Where do we graph that? Is it on the left, in the right, in the middle? Well, Z equals 0 is in the middle. I have Z equals 1.96. So 2.9 is going to be farther over here. So we're in the tails and we're happy. Because if we're in the tails, we can say, okay, we have a significant difference. And we want a significant difference because we always set these up that we want to reject the null hypothesis. We want to reject our guess that there's no difference between these. So we're in the tails, we reject the null. We say, hey, there's a significant difference. Opinions have changed, or we find evidence that opinions have changed. So we have evidence to support our alternative hypothesis. We can't say we proved it because we don't have enough data, but we support it. We think it's possibly true. All right, if we were to do a p-value test, I would look up my z-score, and this would give me a p equals, actually, let me do big P. Big P equals 0.0038. And we want this to be less than the area in our tails, which was 0.025. Happy face. That was really bad happy face. So our p-value approach should always compare. It should give us the same result as the classical approach. I don't think one approach is any better than the other. They're just a little bit different. P-value gives you a little more exact answer, but in the end, you're just going to say, hey, we found a difference, and that's that. Okay. I have a sheet of, I think, 5 examples. Some of these are going to be significant. Some of them are not. So let me hand it out. Too much.